Okay friends, this is again paper PH 6503 Unit 2 Solid State Physics by Dr. M.R. Gadhvi. In the last lecture, we have ended the discussion that there is a change in the frequency, and that frequency, which is commonly known as Larmor frequency, and that variation in frequency is represented by the delta omega. The amount of change of frequency will be equivalent to the minus EB by twice of m, where E and m are constant, so only the change in frequency strongly depend on the applied magnetic field. More applied magnetic field, there is a more change, and the more change that is represented by delta omega. Now what kind of the change it would be? So they said that the positive sign and the negative sign in omega 0, which indicate the electrons whose orbital momentum are parallel to the field, will slow down the frequency of precession, and those moments which are anti-parallel will speed up by the amount of EB by m. And this discussion result in conclusion about the Larmor theorem. The frequency change gives rise to the magnetic polarization or simply the magnetization, and this variations, that is delta omega, is the root cause of the indication of the dimagnetism or the magnetization of a dimagnetic material or the magnetic polarity of a dimagnetic material. The delta omega is in general it's a 2 pi f, but there is a delta function is variable to the frequency, so it's a 2 pi nu, and that is minus EB by twice of m. And if I will equate with the frequency or change in frequency, then I mean the linear frequency, then it would be the EB. This is a change in angular frequency, this is a change in linear frequency, then it's a minus EB by 4 pi m. And this change is corresponding to the magnetic moment of an electron is correlate with the change in the magnetic moment of an electron, and then I can find it out. It is nothing but the cause of production in the change in magnetization, and therefore I can equate the change in magnetization is equal to IA, that is I, that is a current because of a motion of electron in orbital motion, and the cross sectional area of that orbital, that is A. So if I will consider it's a circular one, so pi r square, and current will be given by E by T. Now the change in 1 over T, that is a frequency, so it would be the F, and that F is basically a changing, so there is a change in, instead of a F it's shown in the previous equation, it's shown as a nu, it's a nu, so it's a 2 pi f, instead of that I am saying it's a 2 pi nu, and instead of a nu there is a change in frequency because of omega 0 plus or minus factor, and then it would be a just a minute, it would be a 1 over T, that frequency is a nu, and inside of a nu, if I want to change the change in magnetization, then it would be a change in frequency. So E will be as it is 1 over T will be written as a F, but instead of a F I will be taken the change in frequency, because I want to know the change in magnetization. So it's a delta nu and pi r square as it is, and therefore delta m is equal to minus E. It's just expanding of this one. Delta nu is from the previous equation, that is EB upon 4 pi m, and this EB upon 4 pi m will become the root cause for the magnetization, or a cause of magnetization in the diamagnetic material. This r is basically a radius of an orbit, and in an atom there could be many orbits. So on summing over all the electron in atom, induce a moment per atom become delta m is equal to minus E square B summation of r square upon 4m. That's why I mentioned on summing over all electrons, सभी इलेक्ट्रॉनों को कैलकुलेट कर लेते हैं, in the atom the induced moment per atom become this much. So per atom contribution of change in magnetic momentum, that would be given by this one, and change of magnetic momentum in direction of a magnetic field, so that would be the change in magnetization, and that's why it's a delta m. Okay, so once you do the summing of these all electrons, and that would be the minus E square B sum of, that is a sigma r square upon 4 pi m, that is summing over all the electrons in an atom, the induced magnetic moment per atom. So when the summation is extended to overall z orbitals of an electrons, so once you are knowing that there are z number of orbitals are there within an atom, so it's better to multiply the sigma of r square by the z of average r square. So now the summation of r square, माने जितनी भी orbits है वो सब के तुम summation कर लो, so that you can equate with basically with the number of orbitals. So where the summation extended overall z orbital electrons. So एक से ज़्यादा आपके पास orbitals है, कितनी orbitals है, z number orbitals है. So that z number of orbitals multiply by the average of the orbitals. आपके पास तो s की orbital है, p की orbital है, उसके बाद d orbitals है, so all having a different diameters. So you take the average of them and the available number of the orbitals. So if you multiply that, that is almost equivalent of summation of the r square. So this is an important concept over here. So with this, if I consider in general an atom is an spherical model, then any orbitals which is which is perpendicular to the z axis but is lying in a x and y plane, then the average radius will be given in terms of x square plus y square, the average x square plus average y square. And if I consider the 100% sphericity of this one, so x square is equal to y square, and therefore it's a twice of x square equal to the average square of the radius. And if I consider the any projection in a atomic space, positioning to the electron which is rotating in an across the orbital, then in general the way position vector is representing position vector r, same way if I consider the average r0 square represent the average radius of an electron around the nucleus. तो मैंने आपको पहले बताया कि s की ऑर्बिटल की सिचुएशन, p की सिचुएशन, d की सिचुएशन, f की सिचुएशंस वो काफ़ी अलग है. So naturally I should go for the average value of the positioning vector, and that would be in case of the sphericity of a atomic model, then I should say the average position vector r0 square is given by the x square plus y square plus z square, and since you applied the sphericity, so it would be the average x square is equal to average y square is equal to average z square, and therefore r0 average I square and average of that would be equivalent to 3 of x square. Same way an orbit which is lying in an xy plane, and over the sum of all the orbitals, one can say average r square is equal to twice of x square. So from this relation and the RHS, that is r0 square relations, we can having the relation between the r0 and the r. This is interesting point to be remember, because आपके पास एक इलेक्ट्रॉन ऑर्बिटल में घूम रहा है, एक वो सिचुएशन है, और कोई भी इलेक्ट्रॉन को आप न्यूक्लियस से प्रोजेक्शन डिफाइन करके कोई भी वेक्टोरोलॉजिकली यू कैन फाइंड इट आउट द पोजीशन वेक्टर in context to that particular electron. So in that case you are getting the r0 and the diameter of orbitals that is given by the r. So एक तो ये सिचुएशन है कि जो जिस ऑर्बिटल में आप घूम रहे हो उसका रेडियस, और दूसरी सिचुएशन है पोजीशनिंग वेक्टर विथ रेफरेंस टू द न्यूक्लियस. सो ये दोनों को कोरिलेट करके r0 को के टर्म्स में मुझे r मिल सकता है. सो r0 square is equal to 3/2 r square. So if you look at the previous equation, then that is a delta m is equal to E square B sigma of r square by 4m. So this sigma r square is replaced by the z of average r square, and now this average r square is replacing in terms of the r zeros, that is the positioning vector of the electron, and that would be that's why r0 can be written as a 3/2 average value of r square. And if I want to replace r0 in terms of r in terms of r0, so it would be 2/3 r0 square on average of that. So that would be 2/3 average r0 square value, that would be giving the net magnetization of a diamagnetic material. So finally my equation of a magnetization will be, if n number is the atoms per meter cube, then the magnetization is given by n. I am multiplying this relation, that is E square Bz 2/3 average value of r0 square divided by 4m. This part will be multiplying by the n. So अगर ये पूछा जाए इक्वेशन, तो आपका ये एक एटम का वन गेट्स एक एटम का सिचुएशन. एंड इफ आई से दैट आई डू हैविंग n number of atoms, then you can having a put in this one. Now what is z? Z is defining the available number of orbitals which are filled by the electrons in the diatomic material. तो पहले तो पूरी सिचुएशन ये हुई थी कि आप सेंट्रीपिटल फोर्स और सेंट्रीपिटल फोर्स और कोलम्बियन फोर्स को इक्वेट कर रहे हो फॉर अ सिंगल एटम. फिर सिंगल एटम में मल्टीपल नंबर ऑफ ऑर्बिटल्स आई, तो दैट इज़ गिवन बाय द जेड आर स्क्वेयर. तो z is basically gives us the number of orbitals in the in an atom. So that z is over here, and b is replaced by the mu 0 h. B is replaced by mu 0 h, so it would be mu 0 h. Why I had converted? Because I want to find it out the equation of a susceptibility. Magnetization per applied unit magnetic field, that is gives the susceptibility. So this h will go over here, and it's a mu 0 n e square and average of r square divided by 6m, and this is the final Langevin formula for a susceptibility of a diamagnetic material On basis of the equation 9.31, we may have a few examples where Z, N and R0 and M will be given. You need to find it out the chi, or in short 1, 2, 3, 4 and 5 4 terminal, because I am considering mass of an electron is a constant, charge of electron is also constant, and you might be knowing mu 0 is also constant. So needed parameter is Z, N and R0, only 3 parameters, and with this one can find it out the any kind of the example. Let me show you over here. There is a chi for a diamagnetic material in order of 10 to the power 6 is also found experimentally true. Assume that one electron and one taking M is equal to 91 point minus 31 kg, R0 is equal to a 0.1 nanometer. Again, let me remind you, R0 is the kind of a position vector pointing out an electrons with context to the nucleus. Okay, and N is equal to the available number of electron density per atom, and electrons Columbian value, and therefore their chi can be written as chi with the negative sign, and negative sign is a tagline of the diamagnetism. And you can see that it's very feeble, very less, minus 3 10 to the power minus a. So experimentally value had find it out for a copper, then it become the minus 9 10 to the power minus 6. So in a way, if you check it up, it is a 3 times lesser value. So it is a big difference, but just let me highlight that one. So summary of the entire discussion is there are no permanent dipole moment, and hence the magnetic effect are small. Since the induced magnetic moment always opposes the applied field, the diamagnetic susceptibility is always negative. Since the induced magnetic moment always opposes the magnetic field, and therefore diamagnetic susceptibility considered to be a negative. It is always temperature independent. A little variation observation is due to a orbital changing slightly with the temperature. So on an average diamagnetic material है वो temperature free रहता है. Although a diamagnetic material are usually referred to a substance with no permanent dipole, magnetic moment induced by an applied field do exist in all substance, and so does the diamagnetism. And this is a very interesting point to be noted. However, in this substance having a permanent dipole and permanent effect due to the usually mask, those due to induced dipole. So this is a very interesting. Let me repeat again. Although the diamagnetic material usually refers to a substance with a permanent dipole's magnetic moment induced by the applied field do exist in all substances, and so does the diamagnetism. However, in substance having a permanent dipole, the magnetic effect due to them usually mask those due to induced dipole moment. इसका मतलब इन शॉर्ट ये हुआ कि पैरामैग्नेटिक मटेरियल में भी ऑर्बिटल मोमेंट की वजह से डायमैग्नेटिज्म is already existing, but the amount of dipole moment contribution in a magnetization is huge compared to this 10 to the power 6 minus order, and therefore the even existence of a diamagnetism in a paramagnetism we overlook because of its feeble contribution. So thank you so much for attending the lecture. This lecture and the previous lecture, lecture 1 and lecture 2, is your syllabus of the exam. I'm so sorry for publishing late, but I hope you will understood my unavoidable circumstances. Thank you so much. All the best for exam.